All right. So let's take a look here. This is our momentum, impulse, and collision review. All right. And so let's see. I'll start with my name, Mr. Mudry. And today is 12/14/2020. All right. So let's see here. This review is for three things: momentum, impulse, and collisions. Okay. Remember, momentum is they use the symbol P for momentum. Nobody knows why, and it's equal to mass times velocity. Impulse is we can abbreviate it I. It's also known as change of momentum. Remember that the triangle means change. Okay. And it's equal to, normally, we can think of it as force times time. But because it's a change in momentum, it could also be equal to mass times a change of velocity. All right. But it can also be equal to a final momentum, we'll call that PF, minus an initial momentum, we'll call that PI. All right. And, well, collisions are when things crash into each other, and there are two types that we'll talk about in a second. All right, so let's see here. Question number one, it says, what is the momentum of a 75 kilogram shopping cart rolling 3 meters per second? So we write down P equals question mark, M equals 75 kilograms, and V equals 30 meters. 3 meters per second. All right. So remember, momentum is like inertia, right? Momentum is how hard it is going to be to stop something. Inertia can be how hard is it going to be to get something to move, but also how hard is it going to be to make something stop. So this is just like a way that we put a number on how hard it is to make something stop. Again, our formula is P equals mv. P is unknown, mass is 75, and velocity is 3, right? And so we multiply 75 times 3, and we get, what are we going to multiply 75 times 3? 225? Is that right? Is that what you got over there, Dominic? All right. Okay, you check my math because I'm not sure. All right. So anyways, so that's just our basic P equals mv, where that's, mass times velocity. All right, next up we got a truck is going 15 meters per second and has a momentum of 34,000 kilogram meters per second. Again, those are our units for momentum. It's just mass times velocity, basically. And it asks us, what's the mass of the truck? Okay, so we're going to write down what we know, 34,000. The mass is unknown, and the velocity is 15 meters per second. Okay, again, we write down our formula and make our substitutions. 34,000 equals mass times 15. Okay, now this time we're not just going to be multiplying together, because we're solving for m instead of for p. So in this case, we have to get the m by itself, and we do that by dividing both sides by 15. And then we ask Google, hey Google, 34,000 divided by 15. Dude, what the heck, Google? Hey Google, 34,000 divided by 15. Good. Did you guys get that the mass equals 2,266.666666666 kilograms. That's what I got. All right, so this is a truck, and that's about almost 5,000-pound truck. Very good. All right, next we've got a driver. They're going 18 meters per second, and they hit another car head on. The driver's head, which has a mass of 8 kilograms, hits an airbag and stops. What is the change in momentum of the driver's head? All right. Now, there's a few things to realize here. At the beginning, the driver's going 18 meters per second, and the head has a mass of 8 kilograms. That means that we can very easily figure out what the momentum is at the beginning. At the end, though, the question is, how much momentum does it have at the end? Well, at the end, the driver's head comes to a stop. And if it comes to a stop, then the momentum is 0. Okay. Now, this is an impulse type of question, which means that we can either use a force times the time, mass times a change in velocity, final momentum minus an initial momentum. Okay, we have all of those choices. What I want to use is I'm going to find our change in momentum is equal to mass times the change in velocity, because we can very easily figure out what that change in velocity is right here. I'll show you how. So our change in momentum is unknown. The mass is 8. The change in velocity is the final velocity minus the initial velocity. Okay, we always do final minus initial. Okay, so in this case, our final is 0 minus our initial, which was 18. So our change in velocity is negative 18 because we slowed down 18. When we make our substitutions, we get delta P equals 8 times negative 18, which works out to be negative 144 kilograms times meters per second. Okay, that's how much the momentum changed. And what's handy is that later on we can figure out how much force was required to cause that change. Okay, and so why don't we do that one next? That one's number 6. Okay, so we're going to use this information here and the question down below. All right. Now, let's see here. The sign is important for momentum. And so that it says negative 144, we're going to want to keep that. Okay. So let's see here. In the next question, it says the head of the driver in question 3 stops in 0.5 seconds when it hits the airbag. What is the force on the head? Okay. So we're going to have 2 calculations here, because the next one says, what is the force if it hits the windshield and stops in 0.01 seconds, which is much faster, right? 100th of a second versus half of a second. That's a 50th of the time, and so that's going to require a lot more force. Anyways, so let's see here. In this case, because we're looking for a force, I'm going to write this down like this. Okay, impulse, which is changing the momentum, is negative 144. And we got that from the question before. The force that's going to be required is unknown. Okay, and remember, when you get in a car crash, you want to minimize the amount of force on your body. Okay, which is one of the reasons why we have airbags. Actually, that's pretty much the only reason we have airbags, right? All right, the time when it hits the airbag is half of a second. Okay, so again, this is force times time equals impulse. So negative 144 equals force times 0.5. Okay, now be careful when you're solving this. Okay, a lot of people want to divide by 2 or something like that, because we have this 0.5 right in here, which is like half. but you don't want to do that. So just be very careful. Divide both sides by 0.5. You know, you go 144 divided by 0.5, and you get a force of, force of negative, what is it? 288 newtons. Why isn't my screen working? 288 newtons to the left. Okay? Which means, like, you know, the person's head, this is their head, was moving this way, and the airbag pushed back with the force that way. Okay? All right. Now, so that's a force of 288 newtons. All right, is that a big force? I don't know, but let's compare it to the next one. Okay, in the next one, we have the same impulse, okay, because we have the same amount of same change of momentum. We have negative 144 for our impulse. The force is unknown. Now, you might think that we have a force up above, but no, because we're looking at a different scenario where the time that it took to stop the head was much shorter, 0.01 seconds, which is a hundredth of a second. So again, we use I equals force times time, sorry, and we got negative 144 equals force times 0.01. Okay, and just like before, we want to be very careful. Make sure you're dividing the right numbers. 0.01. Let's cancel. Okay, and 144 divided by 0.01 is, if I'm not mistaken, negative 14,400 newtons. Now, this orange one is the force if you hit the windshield, 14,000 newtons. And the green one is the force if you hit the airbag. So clearly a much bigger force if you are striking something solid like the windshield. All right. There's another good reason to wear a seatbelt. All right, let's see here. I'm going to upload all of this to our Google Classroom also so you can see it. Number 4, a person pushes a 1,500 kilogram car with a force of 1,000 newtons for 5 seconds. What is the impulse on the car? Remember, again, there's lots of different ways to calculate an impulse, but our main one is force times time equals impulse. So I is unknown. The force is 1,000 newtons. And the time is 5 seconds. Okay, now, that's not how we abbreviate seconds. 5S. Okay, now, you may be asking, but hey, Mr. Mudry, what about this 1,500 up here? Right? That 1,500 is unused. Unused disinformation, fake news, trying to mess you up. All right? So, yeah, that's not an important value in this question. So anyways, we take our force, 1,000, and multiply it times our time, and we get 5,000 Newton seconds. Okay, now those are weird units, right? Newton seconds, when we're used to using kilograms times meters per second for questions involving momentum. That's true, okay? But a Newton is actually a unit that's made up of mass times acceleration, which is kilograms times meters per second squared, which when we take that, newtons, and multiply that times seconds, that seconds cancels there, and we're still left with our kilogram meters per second. So a Newton second is actually the same thing as a kilogram meter per second. But that's just weird stuff about units, and Mr. Mudry likes that. All right, cool. Number 5, it says, what force is required to increase the momentum of a 75 kilogram cart from 150 kilogram meters per second to 750 kilogram meters per second in 15 seconds? All right. So again, let's see here. Change in momentum is the same thing as impulse. Okay, and when we do change of momentum, we do P final minus P initial. And that equals our impulse. And our impulse is equal to force times time. This is my favorite stuff. I don't know. This is my favorite stuff. Anyways, let's see here. So, right, we've got two values for momentum. It says it want to increase the momentum of the cart, where again, we've got a mass in here that we don't need. It's just in there messing you up. Okay, but we do have a value for momentum. That's an initial, and that's our final right there. So let's put our final first, 750 minus our initial, 150. And that will solve for that right now. 750 minus 150 is 600. So that's our change in momentum, right? It was a positive change in momentum, which must mean that this thing is speeding up. Okay. Anyways, that equals force times time. Our value for time is 15 seconds. All right. And then we go, hey, Google, what's 600 divided by 15? And we get, when we divide by 15 on both sides, the force is 40 newtons, which is about the weight of 40 apples. All right, next up, we have a rubber ball is thrown at 12 meters per second and experiences a perfectly inelastic collision with a wall. What is the velocity of the ball after the collision? All right, what you need to know is that there are two types of collisions. Okay, there is a type that's called elastic and another type that's called inelastic. Elastic. Okay, and in an elastic collision, the thing bounces. It bounces. It does. It does not stick. It does not become deformed. It just bounces right off. Okay? And one other thing, kinetic energy is conserved. Okay, that's in an elastic collision when things bounce. Okay, and they don't stick together. Examples of this: super bouncy ball, right? Or even pool balls, right? Billiard balls are very elastic in the way that they bounce off of each other. Okay, and they don't stick. They are not permanently deformed. They just strike and bounce away. In inelastic collisions, the things that crash into each other stick together. Okay, and they may stick together and move away together. They may become deformed. Okay, they may heat up. They may do those kinds of things that waste energy. Anyways, in these cases, kinetic energy is not conserved, meaning that the kinetic energy that the rubber ball had before is different than the kinetic energy it has after its collision. All right. An example of this might be, I don't know, what's something you throw in sticks? Sticky hand. Sticky hand toy. Okay. Or two train cars. Like the train cars, they crash into each other and they hook together. Okay, might be an example of an inelastic collision. All right, but in this example, it says we have a rubber ball that's thrown and experiences a perfectly inelastic collision with the wall, which means that the ball was going really fast, and this is like situation 1. Right? Moments later, it's stuck on the wall. Okay? Before, it had a velocity of 12 meters per second, and after, it has a velocity of 0 meters per second. Because it doesn't bounce, it just sticks to the wall. Okay? If it was, this right here is inelastic. Okay, off here. If it was elastic, I'll just redraw it with this color, then the ball would have a 12 meter per second velocity, be going this way, hit the wall, right, and then bounce off going the other direction with a velocity of negative 12 meters per second because it's going the opposite direction. This is elastic. Okay, 1, 2. Okay, it bounces off and goes the other direction. That's elastic. Anyways, next up. All right, number 8, it asks, why is more force applied when an object bounces? When an object bounces, right, it's coming down to the ground, right, and the ground has to apply the force to stop it, but it also has to apply the force to make the ball go back up. Okay, whereas if it just hit the ground and stopped, then the ground only has to apply the force to stop it. So we could say surface must apply enough force to stop and send the ball back up. All right. Is kinetic energy conserved in all types of collisions? You might think so. But when we look at this inelastic collision here, we had a bunch of kinetic energy in this ball that's moving, right, as it's moving this direction. But when it hits the wall and stops, a lot. But when it hits the wall and stops, the kinetic energy becomes 0, which means that the kinetic energy is not conserved. In elastic collisions, because it bounces off and is traveling the same speed but in the opposite direction, kinetic energy is conserved. So is kinetic energy conserved in all types of collisions? No. No. Ke is only conserved in elastic collisions. All right, only in elastic collisions when the things bounce. All right, and this last question is a doozy. In this last question, we have a large truck. That's a 3,000 kilogram truck, and it's going 20 meters per second. Okay, it hits a smaller car that's going 10 meters per second in the same direction. So we have let's see here. I'm going to draw a really amazing truck. Okay, there's our truck. Right, it has a mass of 3,000 kilograms, and it has a velocity of, let's go this way, 20 meters per second. It's going to crash into a smaller car. Okay, that has a mass of 700 kilograms and is going, actually, I should make that arrow, might mean that vector smaller, 10 meters per second. Okay, after the collision, they are, it says if it is an inelastic collision, meaning they stick together, what is the velocity of the two vehicles after the collision? So the important thing is, in collisions, momentum is conserved. Kinetic energy is not conserved. Okay? Kinetic energy is not conserved because in an inelastic collision, things like the things that collide into each other may change shape, and changing shape takes energy. They may generate heat, that takes energy. There may be sound, that takes energy. Okay, but so energy is not conserved, but the momentum is, which means that the total momentum of the two vehicles before is equal to the total momentum after. So we need to find out the momentum of the truck, which was 3,000 times 20, plus the momentum of the car, which is 700 times 10. Okay, and add those values together. So 3,000 times 20 is 60,000, plus 7,000 for the car gives us a momentum of 67,000. Okay, that is equal to the momentum of the car and the truck stuck together after the collision. So their mass after the collision is 3,000 plus 700, which is this, 3,700, and their velocity is unknown. Okay, they're gonna be moving away together. Okay, the way that we solve for this, divide both sides by 3,700, and we ask Google, hey Google, 67,000 divided by 3,700. Dude, you just heard me, Google. Hey Google, 37,000 divided by, shoot. Hey Google. Stop. Hey Google, 67,000 divided by 3,700. There we go. And we find out that the velocity would be 18.1. So again, before the collision, the truck had a velocity of 20. After the collision with a slower car, it has a velocity of 18.8. The car, on the other hand, which only had a velocity of 10, after the collision has a velocity of 18.8 as well. So the truck slows down a bit, the car speeds up a bit, actually quite a bit, because the car speeds up because it had so much less mass than the truck. Okay, now if the car was going in the opposite direction, then instead of its momentum being a positive 700, let's leave the truck's momentum is the same. Oh my goodness. The truck's momentum is the same. 3,000 times 20, which is 60,000. But the car still has its 700 kilogram mass, but it's negative 10 for its velocity. So it's minus 7,000 equals 3,700 feet. Okay, so we'll combine these two terms together. We get 53,000 equals 3,700 v. Divide both sides by 3,700, which is like 14 point something. I'm not even going to ask Google. Just type it in. 53,000 divided by 3,700 equals, yes. Oops. 14.32. 32 meters per second. So there was a much greater speed change in the second case because the car in that case was going towards the truck instead of away from the truck. So there was a greater speed change and a much, and the car's going to be in a lot of trouble. Anyways, I'm going to upload this to, what do you call it? Our Google Classroom. I think if it doesn't completely, we'll just wait and see if it gets back. Yes. All right. Second. Everybody. Let's see if I can tell this thing to stop.